Unit 2 on Introduction to Fracture Mechanics of Entity Mentorship Program consists of following subtopics, starting with Introduction, Fracture Mechanics, Stress Intensity Vector, Crack Tip Plasticity, Fracture Toughness, and R-curve. Today in this video, we'll see the introduction part. Usually, engineering materials such as metals and their alloys generally contain a variety of defects which act as stress ragers on micro scale. Examples of such defects are pores or voids, slag particles, inclusions, brittle particles, either fractured or intact. The stress concentration effect of these defects is to induce cracking under service load. Cracks on a micro scale can be, for all practical purposes, considered inherent in a structural component, and failure results in service generally as a consequence of these cracks. Cracks may exist in a structural component due to various processes and fabrications. Cracks may also form and grow due to fluctuating stress and strain histories experienced during its operation. The growth of crack may be enhanced considerably if the component is exposed to corrosive environment. Accident damages also could be the source of cracking. All engineering components and structures contain geometrical discontinuities, threaded connections, windows in aircraft fuselage, keyways in shaft, teeth of gear wheels, etc., to name a few. The size and shape of these features are important since they determine the strength of the defect. Conventionally, the strength of components and structures containing defect is assessed by evaluating the stress concentration caused by the discontinuity features. However, such conventional approach would give erroneous answers if the geometrical discontinuities features are very sharp radii. So, fracture mechanics can be divided into linear elastic fracture mechanics and elastoplastic fracture mechanics. Linear elastic fracture mechanics is based on the application of the theory of elasticity to bodies containing cracks or defects. The assumptions used in elasticity are also inherent in the theory of linear elastic fracture mechanics, namely small displacement and general linearity between stresses and strains. LEFM gives excellent results for brittle elastic materials like high-strength steel, glass, ice, concrete, and so on. However, for ductile materials like low-carbon steel, stainless steel, certain aluminum alloys, and polymers, plasticity will always precede fracture. Nevertheless, when the load is low enough, linear fracture mechanics continues to provide a good approximation to the physical reality. Thank you.